next speaker is Yuxin Chen from Princeton.
Thank you for the invitation. And it's my great pleasure to be participating in this great workshop. Today my talk is about an example of a very interesting phenomenon happening in a lot of non-convex optimization algorithms. And this is joint work with Tongma Kaizhen Wang from Princeton Orphy and Yuejie Chi from Carnegie Mellon. So non-convex estimation problems really permeate almost all fields of science and engineering. So there's a lot of variety of applications ranging from matrix completion, deconvolution to even deep learning. If you look at the empirical risk function or the negative log likelihood function that you are interested, usually these functions are highly non-convex. So this gives rise to a lot of challenges when we try to solve problems of this kind. In particular, non-convexity will result in a lot of computational issues there. So the good thing is that not all of the non-convex problems are equally difficult. For many of the cases, if we are able to exploit certain statistical models underlying the problems we have, actually we might actually see some news that's much better than we thought. For example, we might be seeing some benign landscape for many of the problems we are interested in. And this actually gives us a lot of hope in designing efficient algorithms that can, as long as we are able to exploit the statistical properties or the geometry in an appropriate way. So this talk is basically about how we can use statistical models to help us understand the non-convex optimization algorithms. So the goal here is about a fast non-convex optimization algorithms. So typically, if you want to have a fast algorithm, and this is a typical paradigm that people have been using. For example, the first stage, so this is a two-stage algorithm. The first stage, we try to use some method to find an initial point within the so-called basin of attraction. And the next step is that we try to run some iterative procedures until we convergence. As long as you are careful enough, and you might be able to get the desired solution in very quickly. Okay, however, since this is a non-convex problem, typically, even if you are looking at a local region surrounding the global solution, the landscape actually is also much more volatile than we thought. And in fact, there's a lot more fluctuation compared to the standard like quadratic function. So actually, we need to be very careful, even we are within the local region. And this is one of the motivation for a lot of prior work on all of these problems. So in prior work, typically certain kind of regularization is recommended in order to either to stabilize or regularize the search direction so that even within this local region, we can actually converge fast. And let me just give you some examples. For example, for the phase retrieval problems, people have been suggesting that we can use some sort of truncation or trimming procedure to help accelerate the gradient descent. For matrix completion, for blind deconvolution, for these problems actually, starting from Andrea, and it has been suggested that maybe we can, rather than running the optimization based on the original loss function, maybe we can actually look at some regularized loss function by adding some penalty terms there, and to help us get to a more stable trajectory of the gradient descent algorithm. Or the other way is to enforce some sort of projection to help us with this. Okay, so there's already a lot of theory about regularized version of the optimization algorithms, but in comparison, the unregularized version of the, let's say, gradient methods are much, much less understood. For example, take a matrix completion and blind deconvolution, for example. There's almost no theory talking about unregularized version of the gradient methods. And the situation for phase retrieval is slightly better. So we have results for unregularized version, but the computational cost there is highly suboptimal compared to the regularized version. So it's much
hard here with regards to the last two.
Sorry?
No theory. I think it's a bit of an overstatement.
Okay, so I don't know. Actually, maybe there is some theory, but all of the theory based on the regularized version of the cost function, or some sort of extra, like for example, like in Jason's paper about this global geometry thing, And they are changing the empirical loss function to be some regularized version in order to say something about the gradient descent. Okay, maybe I'm too extreme, but as far as I know, yeah. So yeah.
There is. There still are, and it's true that for exactly matrix completion there's a case, but if you slightly, if you look at slightly more general problems, or you know.
Oh, yeah. For matrix sensing, there is a way to do this. I think just for matrix completion, not.
Matrix completion without restricting the rank. Again, there's theory without regularization. So it's.
Yeah, no, I agree with that. Yeah, I agree with that. Just usually, if you look at more general version of matrix factorization problem, let's say, and there is a way to do this. Yeah, at least there's some theories for that. Just say for matrix completion things are.
Yeah, there's also that feeling if you start with an appropriate point, then there's so work from groups in Austin.
Even earlier, right? I mean, this stuff like Montanari is looking at this like manifold learning, well, whatever it was called. Andrea's not here. Where is he?
Yeah.
Hey, man.
Sorry. No. No. I mean the regularized version is suggested by Andrea first. So I mean, a lot of people follow this one actually. So yeah. Anyway, so okay. So yep. Okay. So now the question is really about whether we can use an unregularized version of gradient descent to achieve at least the same computational complexity as similar to the regularized version. Okay. So in this talk, I'm unable to present the ground theory about this. So let me just use phase retrieval as a guiding thread to present all of the ideas here. And all of these ideas actually carry out to matrix completion and blind deconvolution problems.
What's the benefit of doing unregularized version instead?
What's a bit? So first of all, usually these regularization methods are highly so it's very much tailored to the very specific statistical models there. So practically, usually, if you run these things, usually there's almost no role of this regularization part. Even, for example, like in Andreas' Nonconvex manifold gradient descent method that he used, if you run it really, actually, this regularization term has never been used in practice, actually. So they are enforcing some extra term. So if something like your trajectory go out of some comfort zone, then this will be effective. But practically, actually, this is not really something that has ever been effective. So I think a good understanding about the unregularized version could be more could say something that's more practical. So let me focus on phase retrieval and then explain all of the ideas here. The problem is the following. So suppose I have a ground true x, which is n-dimensional. And then I observe a lot of quadratic equations about the unknown object. So let's say I have m of them. And the goal is to recover x sharp from this quadratic system of equations. Okay, and so there has already a lot of work on this problem, and starting from 2014, Emmanuel, Xiaodong, and Madi has proposed a so-called Wortinger flow for solving this problem. And they look at this empirical loss objective functions. So this is sort of like a mean square error for the problem. And then we follow, they follow a two-stage approach. First, you use spectral method to obtain initialization. After that, they use something called Wortinger gradient iterations and run it until convergence. If you focus on the real case, essentially this is like a vanilla gradient descent method. So, and there has already been some theory obtained by Emmanuel, Xiaodong, and Madi. So my goal is to try to first examine what they have using some standard optimization theory, and then try to see whether this is already matches practice or not. Okay, so since this is a vanilla gradient descent method, at least locally, so let's try to look at what gradient optimization people can tell us about this problem. And usually, if we want to say something converges fast, there are usually two standard conditions that determine the linear convergence of a gradient descent algorithm. So one is strong convexity, at least in the restricted sense. Another is smoothness, and also maybe in the restricted sense. So it is well known that if we just run a gradient descent for such a nice function, which is alpha strongly convex and beta smooth, and we have L2 error contraction there, and the error, the contraction rate is essentially just determined by beta over alpha, which is the condition number. So essentially, if we can always make sure that the iterates are always within a nice region, and then we can say that this algorithm can attain epsilon accuracy within roughly beta over alpha times some logarithmic factor, the number of iterations. So this is what gradient descent theory can tell us. Okay, so now let's try to apply this theory to the phase retrieval problem and see what this can tell us. Okay. So let's again look at some random models. So suppose that we have a Gaussian design. Each of the sampling vector is ID Gaussian. Let's start with the simplest case. Let's say we have infinite samples, so it becomes a nice, becomes a very nice landscape. In fact, if you look at the Hessian, the expected Hessian in the local region, and you can prove that this is actually a very, very well-conditioned function locally, and it's also strongly convex. And as a result, if you look at the infinite sample case, the Working flow actually converges to the truth within logarithmic iterations. Now the issue arises when we move on to the more realistic situation where we have a finite number of samples. So when the number of samples you have is just slightly above the information limits. Now the function, the Hessian, with high probability, the Hessian is still a strongly convex function, at least locally. Now the issue is that the condition number is extremely bad, at least for this Gaussian design model. And the condition number in this regime can be as large as n. N is the number of unknowns we have. So this is not a good news because this is essentially saying that the number of iterations taken to converge might actually depend on the problem size. In fact, just applying this theory, we can say that Working flow attains epsilon accuracy within roughly n iterations. And this is exactly the theory presented by Candice and his co-authors. So the question now is, of course, that now we need n iterations to converge. This seems to be very slow. So whether we have a way to accelerate it. And the answer definitely is yes. And so you can use some sort of regularized version of the gradient descent to achieve much faster convergence. But this is not the focus of this talk. The talk is about whether this theory really matches what's happening in practice, which is a theory that's basically based on the generic optimization theory. So let's take a closer inspection of this problem and see what's happening. So Working flow, we say that it's slow because it converges roughly within n iterations. And the reason that it converges within n iterations is that the step size is going to be very small. So we take the step size according to the smoothness parameter. In this case, it's 1 over n. So it's a vanishingly small step size. And this choice, this step size choice, is essentially just suggested by generic optimization theory. Or put another way, this is sort of like suggested by the worst case optimization theory. And the question is whether this kind of optimization theory really captures what's going on, at least in this problem. So in order to answer this question, so let me first collect some numerical evidence and as an illustration. So let's look at, let's run a Working flow and for different problem sizes ranging from 20 to 1,000. And let's fix the step size to be 0.1 rather than taking it to be 1 over n. But it seems that for all of the cases, actually, the algorithm actually converges very fast. In fact, for most of the cases, actually, within 200 iterations, you always get like 5-digit accuracy or something. So it seems that even the vanilla version of gradient descent actually works could work much more aggressively than was suggested by the working flow theory. So now the question is why this efficiency is unexplained by the existing theory. Okay, so in order to answer this question, so let's take a closer look on the gradient descent theory and see what goes wrong here. Okay, so as we mentioned, we would like to make sure that our iterates are within a nice region, and this is a region that has sort of like restricted strong convexity and smoothness. And if we look at the phase retrieval problem, this region is characterized by the following conditions. First of all, the point should not be too far away from the ground truth. So think about it as a L2 ball surrounding the solution. Next thing is probably even more important is that actually we also want to make sure that x, the point x, is not going to be too aligned with any of the sampling vectors. So in some sense, this is saying that it needs to be incoherent with the sampling vector. For example, if we look at the region of points that is incoherent with respect to the first sampling vector, and then you get this strip. If you have another sampling vector, essentially, this will give you a polytope. So eventually, the region that enjoy nice geometry, it's going to be something like a polytope rather than just an L2 ball. Okay. So now we can see what goes wrong in the existing theory. So in the prior theory, it basically says that if the region that you have it's an L2 ball, and because we can make sure that there is L2 contraction there, so after a few iterations, actually we have L2 contractions, so we always stay within this nice region. Eventually, and this can converge. But if the nice region that we have is like a polytope, then think some bad issues happen. For example, if you start within this polytope, and if you run it for one gradient iteration, you can make sure that we have L2 contraction, but you have no way to make sure that this will still stay within the polytope of interest. And as long as you jump out of this polytope, and then the gradient method might actually overshoot. And if you overshoot, eventually, and this will diverge. Okay, so essentially, almost all of the prior work have been suggesting some regularization method in order to make sure that the iterates are always within the nice region. And the finding of this work is the following. So even though the generic optimization theory cannot make sure that we are within this region, and using some statistical tools, if you look at the probabilistic model in a more careful way, we can actually make sure that the iterates will always stay within this nice region throughout the execution of the entire algorithm. Okay. So this becomes a nice thing because if you're always staying within this polytope, and we can make sure that the algorithm will never jump out of it, and so it will not overshoot. And as a result, and this gives us a very good contraction properties. Okay, so the key message here is that the gradient descent, even the vanilla version, can implicitly force all of the iterates to stay within an incoherence region, and which is the key thing that enable fast convergence of the gradient descent methods. So more formally, the theorem is like the following. So we can make sure under ID Gaussian design, the Wortinger flow will always satisfy the iterates will always satisfy some sort of incoherence condition, and with this, we can obtain a very fast convergence. So essentially, it converges within logarithmic iterations, even when the sample size is not much larger than the information theoretic limits. So we are able to adopt a much more aggressive step size, and we have a computational complexity that's much better than the existing theory. just maybe 1 minute explaining the key idea about showing all of this. Since our goal is to say that the iterates will always stay incoherent with each of the sampling vector. So essentially, this is sort of like a point-wise L infinity norm bound. So to do this, I'm going to introduce some auxiliary sequence. Let's call it XTL. And this is constructed by dropping out a single sample from all of the measurements we have. So suppose I'm dropping the L's measurements. I'm not going to use it, but I run the same algorithm on this new set of samples. So why this is interesting? Because if you drop one sample, so the iterate has never seen, let's say, A1. And then with high probability, this A1 is always going to be incoherent with all of the points here. So with high probability, this will be true. And since we are only dropping one sample, so the new iterates and the true iterates are going to be very, very close to each other due to some stability guarantee. And as a result, since they are very close and one of them is very incoherent with respect to the sampling vector, so we can say that the entire sequence, the true sequence, is also going to be very incoherent with the sampling vector. And it turns out that this recipe can be very general. So let me briefly mention something about matrix completion. So I think probably everybody knows what matrix completion is. Essentially, you have a low-rank matrix. You observe partial entries about this matrix, and you want to fill in all the unseen entries. And usually, we can look at the empirical risk function like this and try to solve this non-convex optimization problems. And existing theory, starting from Andreas, so and then usually includes some regularized loss function by adding some penalty term to the original empirical loss function. Or you can use like what Professor Wainwright has done, is enforce some extra projection operation to enforce incoherence. And what we can say is that none of these is really necessary. Actually, even practically, none of these is necessary. So what we are going to do is basically just run a vanilla gradient descent with spectral initialization, and then we can show that a very fast convergence of this vanilla gradient algorithms. And what we can say is that, so if you look at the error terms, the convergence happens with not only with respect to, let's say, the Euclidean norm, but it also happens with respect to, let's say, the spectral norm. It also happens with respect to the L2 L infinity norm, in this case, which actually is exactly how we define the incoherence for the matrix completion problem. Okay, so a byproduct of all of these analyses is actually can show that in the noisy case, if you just run vanilla gradient descent, we're able to control the entry-wise error in an optimal way. So you achieve the minimax bound in terms of the entry-wise error. So the errors are really spread out across all of the entries.
Get these with spectral?
No, spectral, for example, even the noiseless case, spectral method, it doesn't have a zero error. So you need to refine it in order to get zero error. So yeah. But for convex or non-convex optimization, at least in the noiseless case, you can always get the any level of any resolution you want. So this also extends to other problems like blind deconvolution. I don't have time to talk about this. The final slide is this. So the incoherence region, as I plot here, it looks like a polytope. But this is really an illustration in the two-dimensional space. You really need to think about it in a high-dimensional world. So your mental representation probably should be sort of like this hyperbolic drawing rather than this polytope thing. So which is basically saying that the region actually is vanishingly small compared to the L2 ball. Even though this is vanishingly small, you can still make sure that the entire iterate sequence can stay within this convex set. Okay, so just to summarize, this is some nice thing about gradient descent. So even without any extra regularization, you achieve very fast computational complexity, very, very good computational complexity. And as a byproduct, we are able to obtain entry-wise error control for non-convex algorithms. And the paper is on arXiv. Yep, thank you.
Yeah, so if you have, say you're just optimizing a quadratic form like with gradient descent, then you're converging very quickly along eigenvalues, eigenvectors with eigenvalues which are large, and very slowly for the small ones.
Yeah.
So somehow if your space is aligned with the top eigenvalues, you're converging very well, and your gradient descent is very fast. But the bounds actually tune the worst one.
Yes, it's for the worst bound.
How does it relate to what you're going to see?
So you look at the worst case. So there is a region where some of the points, there's the region with like within the L2 ball. Some of the points are very bad. So so first of all, I would like to say that all of these happen when you have spectral initialization. So with this particular initialization method, you're able to make sure that even when you start the algorithm, your starting point is also going to be in some region that has nice geometry. So you never hit the bad region, actually. And then with high probability, with this initial guess, you can make sure that your follow-up iterates will also stay within the nice region rather than going to this bizarre region that has a bad geometry there. So
But does it relate to some spectral property of this?
Does it relate to? Not really. Well, it does relate to some spectral property because you want to make sure that at least there are sufficiently many points. At least So if you have infinite samples, and you need to make sure that there's some sufficiently good spectral property there in order to have a good convergence. But the tricky thing is that if you have finite samples and they do not necessarily converge to the case at the population level, so you see a lot of fluctuation there in the finite sample case. And that is the part that you need to deal with. But definitely we need some spectral property there, and even in the infinite sample case.
So could you separate for me which results you actually need IID Gaussian measurements and for which you actually need only the incoherence of the measurement?
Most of the, okay, so this is so for matrix completion, what does it mean by IID Gaussian here actually for?
Oh, I was talking about
the phase retrieval one. Phase retrieval one. So far, we only prove it for IID Gaussian or IID sub-Gaussian. I don't think they are crucial. I think if you have like sort of like sub-Gaussian rows, not necessarily IID sub-Gaussian measurements, I think it should work. But
just have incoherence, is that?
Just incoherent, that would be tricky because we need to use some okay. So let me put it this way. If you only have a deterministic condition like on incoherence, probably this will not work. But if you, let's say, I give you a dictionary, you know this dictionary is incoherent, but I randomly sample a few of them from that, maybe this will work. Yeah. But in general, I don't think the deterministic condition is.
Okay, let's thank Yuxin.